Hi, everybody. I'm going to actually review the two problems from the previous day, just so that anyone who either forgets or was not here is able to get caught up with everyone else on these problems, because these will be covered on the quiz. Remember that the wavelength and the frequency of light are related through this equation, the speed. Oops, hold on. Did not have a pen, had a laser pointer. I don't want that. The speed of light is equal to the wavelength of the light times the frequency of the light. Okay. And so if we're trying to calculate the frequency, we're going to divide both sides by the wavelength. And the frequency is going to be equal to the speed of light divided by the wavelength. Now, the speed of light is a constant. It's 3 times 10 to the 8th meters per second. So since the speed of light is expressed in meters per second, we have to take this wavelength, which is 492 nanometers, we have to convert that into meters before we plug it in that problem. Now, the conversion from when we studied metric earlier, nano means 1 times 10 to the negative 9th of the base. So a nanometer is 1 times 10 to the negative 9th meters. We can use that conversion. If we start with the number we want to convert, nanometers, oops, there's one of those little random sidebars that I occasionally get. That's nanometers. Boy, I'm having trouble with this one. I think I'm just going to start it. Let me pick a different color and kind of. Okay, so if we have 492 nanometers, okay, then we want to convert 1 nanometer is equal to 1 times 10 to the negative 9 meters. Let's just ignore that little random sidebar there. If you multiply, you are going to get 4.92 times 10 to the negative 7 meters. That's the wavelength in meters. So we want to plug that in down here. I'm going to go back to my red. 4.92 times 10 to the negative 7 meters. Now, when we divide, you can see that the meters divide out. And when you divide, make sure you're plugging it in your calculator right. Don't hit the times 10. Hit that, remember that double E button kind of replaces the times 10. So make sure you're plugging that in right, this one too. And you should get 6.10 times 10 to the 14. Now, this label right here is per seconds. Per seconds is the same as a hertz. 1/seconds is the same as a hertz. That's a unit of frequency, and we have now found the frequency of that green light. Let's try a problem where we know the frequency, like a radio station, but we don't know the wavelength for their broadcast signal. So again, we can use the equation that we developed earlier. Wavelength times frequency equals the speed. This time we're trying to find the wavelength, so we're going to divide by the frequency. So the wavelength is equal to the speed over the frequency. Speed of light, always, forgot my exponent, was going right to my label. Yep, okay, to the 8th meters per second. Now the frequency up here is in megahertz. We cannot put megahertz at the bottom. The reason we cannot is that, remember that a hertz is equal to a per second, not a megahertz. So we need to do a little converting. 1 megahertz. If you remember mega from our metric time, mega means 1 times 10 to the negative 6, whatever the base is. So a megahertz is equal to 1 times 10 to the 6th hertz. That's supposed to be an H. So let's convert 97.3 megahertz. Definitely got a little crazy there. 1 megahertz is equal to 1 times 10 to the 6th hertz. You multiply through, you get 9.73 times 10 to the 7 hertz. So I'm going to put that number down below here, 9.73 times 10 to the 7 hertz. Now, when I do that, the per seconds and the hertz, they cancel out. And so when I solve and I get my answer, remember to punch your numbers in the calculator right. Use that double E button. You should get 3.08. There's no exponents. And the label that's left is meters. So radio station 97.3, their waves from one peak to the next, that's the distance in their broadcast signal. So those are the problems that we did yesterday. Now, how much energy is carried by each one of these waves? And there's a equation that we can use to calculate the amount of energy. We know they're all moving at the speed of light. But how much energy are they carrying? So a quantum is the minimum amount of energy that can be gained or lost by an atom. Remember that, like, you have, the energy levels, and when an electron moves up an energy level, it gains energy. When it moves down, it loses, okay? Well, the light that it loses when the electron moves down, remember, was electromagnetic radiation. And a particle of light that has no mass, but it carries the energy, is called a photon. Max Planck was a German chemist and physicist who worked out the fact that the frequency of the light is proportional to the energy carried by the photon, and that the proportionality constant was this really small number here, which is called Planck's constant in his honor. Basically, this is, instead of treating light like a wave, and light is a wave, we're looking at the particle or bundle of energy that is carried by that wave. And we can use that equation, and on the test, I will give you the equation, I will give you that number. Okay, you don't have to memorize them. But we can calculate the energy carried by, ooh, that one looks really bad. We can calculate the energy carried by any electromagnetic wave. Let's go with something a little fatter by using that equation. Yeah, I'm kind of liking that, but I want it in a darker color. All right, so we have to calculate the energy. So we're trying to calculate E. We know that Planck's constant is 6.626 times 10 to the negative 34. And that is joule seconds for the label. The frequency is given, and nice, this one I do not have to convert, it's already in hertz, 6.32 times 10 to the 20th hertz. Now remember that hertz means per second, so per second and second, those should cancel. Boy, I thought I did pick yellow. Ooh, the yellow on the purple background makes it look orange. Okay, so I thought I picked the yellow. It's just not going to show up yellow. Let's see what the orange looks like. So we multiply those two numbers, and I'm going to round to 3 sig figs, and I get 4, still looks orange, 4.19 times 10 to the negative 13th. That is a 3. A little hard to make a 3 with the fat highlighter. 13th, and that is joules, because seconds and the per seconds, those canceled out. So that's the amount of energy that each photon would carry in the X-ray. Now, when you go to get an X-ray, at like a medical facility, there's not just one photon. That X-ray is, carrying trillions and millions upon trillions of photons in the beam. This is how much energy is in a single photon. You would have to multiply that by the total number of photons. So this would probably be one of the harder problems that I would expect you to be able to do. Okay. So in this one, you're trying to calculate the energy, but you're starting with the wavelength. They're not in the same equation. You have to use the wavelength to get the frequency and then use the frequency to get the energy. So see, we're going to calculate the frequency because that's C divided by the wavelength. Remember, C is equal to wavelength times frequency. So we're going to divide by the wavelength, and that'll give us the frequency. So C is always 3.00 times 10 to the 8th meters per second. And then the wavelength, you got to convert those nanometers to meters. Remember that? You would take it like times, there's 1 times 10 to the negative 9 meters in every 1 nanometer. When you multiply through, you're going to get 2.25 times 10 to the negative 7 meters. So when you solve that, you are going to get 1.33 times 10 to the 15th hertz. Okay? And so that gives you the frequency, which you can then turn around, and I'm just going to switch colors to maybe make it a little easier to see that it's a different problem. But if we want to calculate the energy, we now plug in the frequency, multiply by Planck's constant, and that's going to give us the energy. So Planck's constant is 6.626 times 10 to the negative 34. And that is joules times seconds. Remember, I will be giving you the constants and the equations. And then we want to plug the frequency in here, 1.33 times 10 to the 15 hertz. The seconds and the hertz will cancel because hertz is per second, so seconds and per seconds cancel. We multiply and we get 8.81 times 10 to the negative 19, and that is joules. Okay? Now we know the energy that is associated with a wave of 225 nanometer wavelength. That wave is carrying a bundle of energy with this many joules in it. So remember on, on the test, okay, that I am going to give you this equation. Now you might have to solve for wavelength or frequency. That's your algebra. I am going to give you this equation. Again, you might know energy and have to solve for frequency. You divide by H. So you got to do your algebra with those equations. You have to match up your units like we did here, or like we did here. This was already in the right units, fortunately. And on the quiz or the test, I will give you the value of C, and I will give you the value of H. Those things that I outlined there, they will be given to you for the quiz next week. But you need to know how to convert nanometers to meters, megahertz to hertz, do the algebra, plug it in your calculator, keep the right sig figs, the right label, right sig figs, right label. So even though I'm giving you the equations and the value of C and the value of H, there's a lot for you to practice and make sure you know how to do. So atomic emission spectra, okay? We're going to take a look at these very soon. Because elements, and I'm just going to draw on here, and then I will erase it. Because elements have, different energy levels, and you can have an electron. Whoops, why did I not get, okay. You can have, oh, why is, that's really weird. Okay, what's going on there? Not sure what's going on there. We'll go with the pen. You can have an electron, like if this is a hydrogen atom, this electron can jump up by absorbing light, and then it can jump back down and give off light. The energy difference between level 2 and level 1, that's how much energy will be given off. And if you know the energy, you can calculate the frequency and the wavelength. The electron could jump up to level 3. From there, it could jump back down to 2, or it could go all the way from 3 down to 1. So you see, you got a couple different energy jumps. You have this one, you have this one, you have this one. The different energy jumps are different sizes, different amounts of energy, which means you're going to get different wavelengths. Every element has a unique number of electrons and a unique arrangement, and the energy jumps are a little bit different for every element. As a result, okay, when you take that element and you hit it with some sort of outside energy source, you will get a unique set of wavelengths and frequencies. It's going to be a unique set of wavelengths and frequencies. And because it's unique, okay, when the electrons go from excited, when they go from up above down to the ground state, because it's unique, each element can be used for identification. Ooh, I see now why my highlighter's not working on the black background. Okay, do you see that? See, it's not writing on the background. It's a highlighter. Learn something every day, don't you? So it's going to be unique for each element. Oh, I kind of like this, coloring in. And because it is unique for each element, okay, it's like a fingerprint, and it can be used for identification. And it occurs when the electrons move, okay, when the electrons move from the excited state, like the outer level, to the ground state, the inner level. We're going to take a look at some atomic emission spectra in the next few days. For now, what you want to concentrate on is being able to do these calculations, because you would be expected to be able to do these on the quiz and on the test. So I hope that has been helpful. Hopefully you can now watch this PowerPoint several times, and you can use the information in it. And if you wait a second, I didn't get that, go back. Okay. If near the end you're forgetting how to convert nanometers to meters, go back to the beginning of that screencast, because I showed you how, and work on doing some practice problems. Good luck.